These are the notes for AP Calculus with some real-world applications of area and volume. So on this one, it says we've got a funnel, has a height of 10 inches, 10 centimeters, has circular cross sections. So you can see right here, we've got these circular cross sections when you slice through this horizontally. And at height h, the radius r is given by this function. So this function, depending on the height, that determines what the radius is. And notice it goes where h is between 0 and 10. So you can think of it like this. This is like the h-axis here. And h is the at height h. So at the very bottom, the height would be 0. And at the top, the height is 10. And so this is the h-axis going that way. And it says units of r and h are centimeters. So it does give you units in this problem. And we're asked to find the volume. So you have to think about, well, how is this funnel created here? If the radius is given by this function. Notice you can see visually, if we just take a rectangle like this, this infinitely thin rectangle, right where that radius is, notice this would be, think of it sideways here, dh, the width of that, and notice we're taking this and revolving it really around the very center here, this h-axis in a way. We're revolving it around that to form this. So you can think of there being like a circular arrow here that revolves around there. So if you think of about this sideways, this is really the disk method, where from the axis of revolution, which is in the very center of the funnel here, to the far end of the rectangle, that's R1. And in this case, there is no R2 because there's no gap between the axis of revolution and our rectangle. So R2 is not needed. So this is the disk method. It just looks different because the rectangle is going horizontally. Instead, we usually see it vertically. So R1, notice that's just the same as lowercase r. It's the same as the radius there, which we're told right here is 1/10 4 plus h squared. And then R2, R sub 2, the inner radius, you could think of it as being 0, or it's basically not needed in this one. There's nothing we need to subtract to find the volume of this funnel. So it's just a little different application of the disk method to find the volume of this funnel. So remember the disk method, it's pi on the outside. And then the integral, well, the region here is like half of this funnel. You can think. Notice it starts at h equals 0. This is all in terms of h, notice. So 0 is our lower limit. And we integrate all these circular disks here all the way from 0 all the way up until where h is 10. And then remember the disk method, it's pi and then r1 squared minus r2 squared. But we don't have an r2 in this case, so it's just r1 squared. So it's basically this whole r1, which they give you, is 1/10 4 plus h squared, that whole thing squared, times dh. So that's the integral using the disk method that will give us the volume of the funnel. Now this is without calculus, so we just have to work it out. So first thing, we have to make this a little simpler so we can integrate it by hand. So we can leave the pi on the outside for now. And let's first square this out. So we'll have integral from 0 to 10. When you square 1/10, you get 1 squared is 1, 10 squared is 100. And then off to the side here, if we have 4 plus h squared, that's like having 4 plus h squared times another 4 plus h squared. So when you multiply those out, that's what we get. 4 times 4 is 16. Plus 4h squared, h squared times 4, plus another 4h squared, and then h squared times h squared is h to the 4th. And then all times dh. So it's a little simple. We can pull the constant as the coefficient out in front. The 1 over 100 times the pi makes it pi over 100. And then we've got the integral from 0 to 10. And then we can combine our like terms, the h squared terms here, 4h squared plus another 4h squared. So now we've just got 16 plus 8h squared plus h to the 4th. And so now, since these are just added together, we can just integrate each one separately. So we have pi over 100 on the outside. And now we're going to integrate it. So the integral of 16 gives you 16h. Plus integrate 8h squared is 8h cubed over 3, plus integrate h to the 4th, h to the 5th over 5, from 0 to 10. And so if we keep simplifying this, pi over 100. I'm not going to multiply it out yet because there's some simplifying we can do to make it a little easier. So I'll just leave this as 16 times 10 plus h times 10 cubed over 3 plus 10 to the 5th over 5. And then minus, when you plug in the 0, all those are going to be 0. So notice all the terms have a 10. So you could factor out a 10, and that works out nicely with a pi over 100 because that will reduce 10 pi over 100. That will just reduce to pi over 10 on the outside. And then notice what we have here now. All that's left of this term is 16. Plus, now we factored out one of the 10s. So now it's just 10 squared, 100 times 8, so that's 800 over 3. Plus, we factored out one of the 10s, so that's 10 to the 4th, which is 10,000, but divided by 5. You can see it off to the side here. We basically have 10 to the 4th, which is 4 tens here. But then it's over 5, so notice that reduces. 5 goes into the 10 twice, and then we just have 10,000. 10 times 10 times 10 is 1,000 times 2, so that's 2,000. And then there's different ways to simplify it from here. But one thing you could do, since it'll work out fairly nicely here, is you can distribute the pi over 10 times all these. So if you do that, then we'll have 16 over 10 pi, 16 pi over 10, but that reduces to 8 pi over, if you divide this by 2, that's 5, plus, notice the 10 goes into 880 times, so now we'd have just 80 pi over 3, plus 10 goes into 2,200 times, so then this should be 200 pi. And then you can just get a common denominator of 15. So multiply this one by 3, that'd be 24 pi over 15, plus multiply this one by 5, that'd be 400 pi over 15, and multiply this one by 15. Well, 15 times 2 is 30, and then add the 2 zeros, so 3,000 pi over 15. And then add those up. You end up with 3,424 pi over 15. And then the units here, since we're talking about volume, it's three-dimensional. Notice it says R and H are in centimeters. This would be centimeters cubed. So we do have specific units, not just units cubed, because they give them to us in the problem. All right, let's take a look at another real-world application one. Similar idea, but it's a little different in how it's worded and what they ask for here. So it says a company designs spinning toys using a family of functions, y equals cx square root of 4 minus x squared, where c is a positive constant. So c may look like a variable, but we have to remember it's a constant throughout the problem. And so they could put different numbers in for c as a positive number, and you'd get different designs for these toys here. And the figure shows the region in the first quadrant, so we're just focusing on just the first quadrant. Bounded by the x-axis, we can see right here, and the graph, they give you the general shape of the graph for some c. So notice they don't label it here and here on the x and y axis because it could depend on what c is. Each spinning toy is shaped in this is in the shape of a solid generator when such a region is revolved around the x-axis. So to generate revolved around the x-axis, and both x and y are measured in inches. So part A just asks for the area of the region in the first quadrant right here, bounded by the x-axis and the graph here for c equals 12. So it gives you a specific c value here, 12. So for area, well, it'd be easiest here. We can't really use a horizontal rectangle because then you'd have to take this function minus itself. So really only a vertical one makes sense in this case. So just draw it somewhere in here. And this is the x-axis, so this would be dx. And the area is just the top minus the bottom. So the key thing, though, is we need to figure out where this region starts and stops. And notice what these points have in common. They have in common the y-coordinate is 0 because they're x-intercepts. So that's how we can find them. We can take our equation here and let y equal 0. So it'd be 0 equals c x square root of 4 minus x squared. And you can see that factors inside the square root. 4 minus x squared is the difference of perfect squares into 2 minus x and 2 plus x. So one of these has to be 0. So for x-intercepts, we would get this one, cx equals 0. C is just some constant, positive constant, so that would just give you x equals 0. When you set 2 minus x equals 0, you get x equals 2. And 2 plus x equals 0, x equals negative 2. However, we know we're in the first quadrant, so x can't be negative here in the first quadrant, so that one doesn't make sense. So that would mean this one is 0, 0, and this one is 2, 0. And we need that because that will give us our lower and upper limits of our integral to find the area. So now we know the integral is from 0 to 2. And then for area, remember, when you have a vertical rectangle, it's just the top minus the bottom. And the top is this function right here. This is our y equals cx square root of 4 minus x squared. The only difference is we have a specific c value, 12. So in this case, that would be 12. Put in for c, x square root of 4 minus x squared dx. And so now we just have to integrate this one by hand. This is also without calculator. So notice, unlike the previous one, there's nothing really to multiply out here. So, and this is remember, there's no product rule for integration. You might think integration by parts, but that really wouldn't work very well because this is the one that you'd try to set f of x equal to take the derivative of. It simplifies, but then this one doesn't integrate easily. So it's not going to really work well with integration by parts. But remember, we just have our u substitution we can use to make it easier. And so let's try that. That's actually the technique that would work here. You would set u equal to the function inside, which is right here, 4 minus square root of x. Sorry, 4 minus x squared, I should say. And then take the derivative of that. Du dx equals negative 2x. Notice the derivative here is not a constant. So this is not one you would use the shortcut on. You can only do that when the derivative is a constant. So we just have to do the traditional u substitution here. So dx would equal du over negative 2x. And when you do regular u substitution with a definite integral, remember we need to convert the lower and upper limits. So let's go ahead and do that to get all in terms of u. These are x values right now. Let's turn them into u values. So when you substitute in 2, notice you get 4 minus 2 squared. That's 4 minus 4, which is 0. And when you substitute in 0, you get 4 minus 0, which is 4. And for now, we still have the 12x. But now we can rewrite this one as the square root of u, since we set u equal to 4 minus x squared. And now we can replace the dx with du over negative 2x. And then we can simplify this. Notice we can pull out the constant 12 divided by negative 2 is negative 6. So you could pull out a negative 6 here. Or, notice the lower and upper limits are now in the wrong order. So you could switch the sign if you want to and make it positive 6. And then flip these to be from 0 to 4. Make it a little simpler. Notice the x's also cancel out here, which is what we want with u substitution. And then you can rewrite square root of u as just u to the 1/2 du. And now we've turned a more complicated integral into a simpler one. So we've got 6. When you integrate u to the 1/2, you get u to the 3/2. Add 1 to the exponent, and dividing by 3/2 is the same as multiplying by 2/3, the reciprocal, from 0 to 4. Then you can pull out the 2/3 along with the 6. That 3 goes into 6 twice. 2 times 2 is 4, or 12 divided by 3 is 4. Either way, it's 4. And then if you switch this to radical form, make it easier to evaluate, u to the 3/2 is the same as the square root of u cubed, from 0 to 4. So then we've got 4. And then when you substitute in 4, you get the square root of 4 cubed, minus when you substitute in 0, it's 0. Square root of 4 is 2. 2 cubed is 8. 8 times 4 gives you 32. And remember, this was area, which is 2-dimensional. And they tell you the units are inches for both x and y, so this would be inches squared if c was 12. All right, then let's take a look at part B. So here we're just focused on the area of this 2-dimensional shape. But now in part B, we're going to actually look for a particular spinning toy. Remember the spinning toys generated when its regions revolved about the x-axis. So now we're actually revolving this around the x-axis here. And we can use our same rectangle. The x. And it says for a particular spinning toy, the volume, they actually tell you what the volume is, pi cubic inches, and it asks, what is the value of c for this spinning toy? So on this one, we have to figure out what the constant is. So we've got pi on the outside. Well, normally, notice this one would involve the disk method, since the rectangle and axis of revolution are perpendicular, right, to each other. And R1 would be from the axis of revolution to the far end of the rectangle. And again, R2 is not needed because there's no gap between our axis and the close end of the rectangle. So R1 is just our function cx square root of 4 minus x squared minus 1 on the bottom of 0. And R2 is either 0 or you can say it's not needed again. And so it tells you the volume is pi. That's the difference here. So we can say pi equals, and then use the disk method. Again, with the disk method, we'd have pi out in front. Integral. Remember, we already found these are from, notice even with the unknown c here, we solved these x-intercepts when we didn't know what c was. So these would still apply 0, 0, and 2, 0 for our lower and upper limits. didn't change. But unlike the area where we just did the top minus the bottom, we use R1 squared, and if there was an R2, it would be minus R2 squared. So we have our whole R1, which we don't know C this time. So it would be C x square root of 4 minus x squared. That whole thing gets squared, whoops, times dx. And the difference is this time we know it's equal to pi. So what you might want to do in your first step, you could do this later also, but if you notice they both have a pi in it, you could just divide both sides by pi so you don't have to keep writing those pi's over and over again. Then the left side would just simplify to be 1 equals. Then we don't have the pi on the outside, and then we can square this in order to make it easier to integrate. So now we just have the integral from 0 to 2. And we'd have to square each of these. So c squared x squared. And when you square this one, it gets rid of the square root, so it just becomes 4 minus x squared. And again, we know this equals 1. So the c, remember, is a positive constant. So because it's a constant, you can actually pull it outside the integral. It's not a variable. And then to make this one easier to integrate, notice all you have to do is just distribute this out. Here we can because now the square root's no longer there. So when you distribute that out, you get 4x squared minus x to the 4th. And now since these are just subtracted, we can just integrate each one separately. So again, we still have 1 equals c squared. And then when you integrate 4x squared, you get 4x cubed over 3. Minus when you integrate x to the 4th, you get x to the 5th over 5. Evaluated from 0 to 2. So we still have 1 equals c squared, our constant on the outside. And then when we substitute in 2, again, you can cube it out here, but I think it'll be easier to simplify if we just write it as 4 2 cubed over 3 minus 2 to the 5th over 5. Because then I think it's a little easier to use factoring here to help you simplify it. You don't have to, but I notice they both have, actually they both have 2 to the 5th if you look at it carefully. 4 is 2 squared, right? And this is 2 cubed. So together that's 2 to the 5th, and so this one's 2 to the 5th also. So you can actually factor out a 2 to the 5th out of both of them. So you have 2 to the 5th times the c squared that's already there. And notice once you factor out that 2 to the 5th, all that's left here, the numerator is just the denominator. So basically we're left with 1 on the numerator, 3 on the 1/3. Minus, same thing here, you're just left with 1/5. So now we can, almost got it here. 1 equals 2 to the 5th is 32. C squared. And then you can just get a common denominator of 15. So multiply this one by 5, that'd be 5/15. And multiply this one by 3, that'd be 3/15. And subtract those, gives you 2/15. And then we've almost got it. 1 equals 32 times 2/15. That becomes 64/15. And now you can see we can solve this for c. Probably the easiest thing to do, divide by 64/15, which is the same as multiplying by 15 over 64. So we get c squared equals 15 over 64 times 1 is just 15 over 64. And then take the square root of both sides. Normally you need plus or minus here, but remember it told us c is a positive constant, so we don't have to worry about the negative. So c would equal, well, 15 doesn't simplify at all, so that's the square root of 15. But square root of 64, that's a perfect square, that just becomes 8. So that is our c value, square root of 15 over 8. That would make the volume of this spinning toy exactly pi. And that concludes the notes for AP Calculus on the topic of these applied problems with area and volume.